Okay, in this particular problem, it tells us that there is a function f that is a Taylor series about x equals 2, and it converges to f of x for all x in that interval. And what it does is it gives us a formula for finding the derivative. So if I want the first derivative, you plug in 1 for n, find the second derivative, etc. And then it also tells us that f of 2 is equal to 1. So part A asks us to find the first 4 terms in the general term. So remember, how do we find the first terms of our series? I'm going to just write the general formula up here. We would start with f of 2, then f prime of 2, x minus 2, second derivative 2, x minus 2 squared over 2 factorial, etc. So we're going to create this series. So f of 2 was given, and that's 1. To find f prime of 2, they give us this formula, so I'm going to just plug in 1 for n. That'll give me f prime of 2. And if I do that, I end up with 2 factorial over 3 to the first. And then I also need that x minus 2. Now, to get to the second derivative, we're going to plug in 2 for n. And if I do that, I end up with 3 factorial over 3 squared. And then I still need that x minus 2 squared over 2 factorial. And I'm going to need one more term. So if I go ahead and plug in the n equals 3 for the third derivative, you get 4 factorial over 3 to the third. And then I need that x minus 2 cubed over 3 factorial. So there's my first 4 general terms. It's a series plus dot, dot, dot. And it also asks for the general term. So we have to figure out a general term. But I don't have to figure out the pattern because they give me a formula for the derivative. So there's my formula for the derivative. And then don't forget, notice what else do we need in our general term? We need this, right? So you also need that x minus 2 to the n over n factorial plus dot, dot, dot. So that's the entire general term. Okay. Part B asks you to find the radius of convergence. Remember, for radius of convergence, there's only 2 ways you can go. Either it can be a geometric series, and we can find that a common ratio, but this is not a geometric series. So the only way we can go is we have to use the ratio test here. And we're going to use the ratio test on the general term, which we figured out up in part A. So this is where now we didn't need to simplify anything here, but now going forward, when I use that general term, this is where maybe you want to clean things up a little bit. Notice that you have an n plus 1 factorial on the top and an n factorial on the bottom. So remember, that's going to simplify to just an n plus 1 on the top. So I'm going to rewrite the general term like this, and then I'm going to use the ratio test on that. So let's do the ratio test. So we take the n plus first term, so replace n with n plus 1 everywhere, and we divide by the nth term, but I'm going to go ahead and turn it into a multiplication problem right away. So there's my setup of the ratio test, and notice a couple things will simplify. So first of all, let's start with the 3's. I'm going to be left with just a 3 to the first on the bottom. The x minus 2 piece, I'm going to be left with just an x minus 2 to the first on the top. And then nothing I can do with the n's yet. But now, once I take the limit as n goes to infinity, because the degrees on the n's are the same, it's going to be the ratio of the lead coefficients. So all you're left with is this. This is my limit. And ratio test says it only converges if that limit is less than 1. And I can go ahead and solve this. Okay, but I don't need to check the endpoints. All it's asking for is that radius of convergence. Remember that radius of convergence is from the center, how many units are you going either direction? So the center of this is 2, and you're just going 3 units either direction. You could actually find it just from this. Once you have it in the form x minus c, this number is going to tell you how many units you go either. So your radius of convergence in this problem is just 3. Okay, I'm going to get rid of this so we can go ahead and do part C here. Okay, part C says there's another function, g, and they give us a couple things about g. They tell us that g of 2 equals 3 And g prime of x is really the same as f of x. And I want the first four terms and the general term for g. Okay, and about x equals 2. So again, that's your clue. So when you write the function for g, you should have, wherever there's an x, you have to have an x minus 2 everywhere. Okay, so first thing, if I know g prime is f of x, in order to get to g, really, that means that we would have to integrate f. Well, I have f up here, so I can just go ahead and take the antiderivative of what I came up with in part A. So let's go ahead and do that. So I'm doing this right now. So the antiderivative 1 will just be x. The second piece, this is just going to stay, right? The 2 factorial over 3, it's just a number. Antiderivative is add 1, divide by the power. Next term, again, all this stays because it's just numbers. And I have x minus 2 to the third over 3. I still have that 2 factorial on the bottom. I'm going to do one more term. These are just numbers. And then I'm going to have x minus 2 to the fourth over 4. And then there was a 3 factorial there. And then I'm going to have a plus dot, dot, dot. But, okay, think back to when we take an antiderivative, there's no bounds, you're going to need a plus c here at the end. Okay, we're going to need to find that c somehow, but what we're going to do is use this point. They're giving us a point to plug in to find that plus c. Okay, again, you have a plus c because we're taking the antiderivative and we're not plugging in bounds. So if I plug in 2 for x, I should get 3 here. Notice this becomes 2, but notice every other term there is an x minus 2. So if I plug in 2 for x, all that becomes 0, so all you're left with is this. So I can figure out that c is actually 1. So I'm going to go ahead and replace this c with 1. Okay. Okay, now this is where it also asks for the general term now. This is where, okay, this looks a little bit complicated. Now let's try to clean things up maybe and we can figure out a general term. First thing I'm going to do is I'm going to group these together and let's write that as x plus 1. And let's see what happens on some of the other ones. So if I look at this, the 2 factorial and 2 drop out. 2 factorial is the same as 2. So really I have x minus 2 squared just over 3. This next term here, okay, 3 times 2 factorial, 3 times 2 times 1, that's really 3 factorial. So all that drops out. And I still have this. The next term, notice 4 factorial is the same as 4 times 3 times 2 times 1, which is everything here. So really you have this. Okay, here's the other thing that's happening here. The problem asked us to find a series about x equals 2. Notice all the x's have an x minus 2 there, but this one. So it has to be written in the form x minus 2. So I'm going to rewrite it and write it as x minus 2. But if I do that, I've changed this problem, but I can write that like this. 3 plus x minus 2 is the same as x plus 1. And notice, isn't that what they told us in the original problem, that g of 2 is 3? So this can be rewritten in this form, and then everything else can stay as is. And now it should be much easier to write that general term. Notice you have an x minus 2 to a power. And then notice the power on the x minus 2 is always less than the power on the 3. So there's my general term. Okay. Lastly, part D asks, does the Taylor series for g converge at x equals negative 2? So g was just the antiderivative of f, so that radius of convergence is going to be the same. So really, we can look back at the radius of convergence, or this interval that we came up with in part A, or in part B. And if you solve this, oops, I'm running out of room here. You end up with this. So -2 is not in that interval, so the answer is no, because the interval of convergence is this.